Okay, we are starting chapter 8. Yay. And I don't know if you just noticed, like, where we are in the book. Like, we've done this much, but only have, like, this much left. You know what I mean? I always think that's a really good feeling when you get to the end of the book and you're like, hey, look at that. We've done so much here. So, lots, right? Crazy, huh? So there's only 4 sections here in lesson chapter 8. But this makes up 22% of the AP test, I think. Something like that. So, you know, it's a big chunk. I can actually tell you. I'll look it up here. Let me see if I can find it. So I can actually tell you how much each, there we go. So unit 8, 20%. No, 15. 15% of the AP test is on this stuff here. So it's definitely a fair chunk. Yeah. So 5, 6, and 8 are the big ones. But we'll go over that. We got time. I'm quite pleased. Here we go. So we're specifically talking about average value of a function, and phrase that will come up a lot. You'll see a lot of practice on this today. We are going to discover the formula for average value. So the average value of a function represents its average height. So we're going to do this a little bit graphically here. We want to draw a horizontal segment from this x equals a to x equals b line, which could represent the average height of f of x on the interval from a to b. So, you know, if you had to approximate this height between of our curve, like we want to find the average. So where would you draw a little horizontal line that would, you know, roughly approximate that function height? We can see it goes high, it goes low. So where would we draw our horizontal line? Maybe about there. Splitting the difference, right? Isn't that what you do? So yeah, that's probably about the average height. Maybe I'm a little high there. Maybe I put it a little lower. I don't know, somewhere about there. Okay. So there is I'm going to connect that all the way over here. All right. So I might call that my f average, my function average, roughly there. Okay. We want to find the area of that rectangle that we formed, the rectangle between A and B. And so what is the width? What is the width of my rectangle? B minus A. Very good. Yeah, it's B minus A. B minus A is the width. And then we have our height, which I don't really know, but that's okay. And we want to then, kind of missing the connection here of what he was doing. I mean, but this is area. Area is the width times the height, right? That's how we find the area of that rectangle. Well, this is also area. When we take an integral, we know that that's the area under the curve. And so that's the area under our function from A to B, right? But it should also, we're going to set that equal to the area of this sort of average height function that we've got. So we want to solve for the average height. This is our average height right here. Our average height, well, all I have to do to get average height by itself is divide by B minus A. So if we divide both sides by our widths, essentially, that's going to give us the average height of the function. So I like to write it as the average, I'm going to use value, the average value of our function is 1 over b minus a times the integral from a to b of f of x dx. So anytime we're asking what's the average value of a function, then all it is the integral with that 1 over b minus a on there. So that gets us sort of the average of those function values, which is kind of nice. You can see it written here. It is important that we understand that our function must be continuous. So that is an important part. It doesn't say that it has to be differentiable, but it does have to have continuity. So that's kind of important. So example 4, find the average value of f of x equals x cubed minus x on the interval from 0 to 2 without using a calculator. Well, if I want the average value, I'm going to call it f average. And f average is just 1 over b minus a. Well, that's our interval, so 2 minus 0, times the integral from 0 to 2 of our function, x cubed minus x dx. 1 over 2 minus 0 is just 1 over 2. And I do know how to integrate this. What is the antiderivative of x cubed? Okay, I'm going to go 1/4 x to the 4th minus 1/2 x squared. And we are taking that from 0 to 2. Again, I still have this 1/2 out in front, and I am going to plug in my 2 to both terms there. 2 to the 4th is 16, over 4 is just 4. Minus, now I'm plugging in the 2 to my second term here, 2 squared is 4, times 1/2 is just 2. So there's the first. Now I'm going to subtract and plug in the 0. 0 to the 4th is 0 minus 0. So, okay, well, that was easy. All right, and then we have 4 minus 2 is 2 times 1/2 is just 1. Of course, if we're thinking about that, this is that function. Here's our function f. And on the interval from 0 to 2, we see our function starts getting quite high, but it does go below the axis a little bit. So if you're thinking about what is the average value, what is that average y value of this function between 0 and 2, you know, I think that splitting it right about there at 1, that looks pretty much like the middle, if you were to sort of imagine what's, you know, to split those areas, really, if you're thinking about it that way. So that kind of makes sense to me. Let's see, we want to use our calculator to find a value of c in the interval between 0 and 2, where f of c equals the average value. So where does f of c equal our average value? Well, if I were to do that, maybe formally I would set that up again, but I don't really need to. I'm going to go ahead and of x cubed minus x dx. Okay, this comes up in AP testing all the time, and Mr. Taylor does a very good job of sort of working us into that sort of thing. But this is find a value of c which equals the average value of the function. So they're asking you to figure out two things. One is this side. We already did that. So we know that the average value is 1. So we could figure all that out, maybe, if we hadn't already done that. So we already know that that equals 1. And we want to do this. So what does this mean? What does f of c mean? Well, all it's doing is saying, hey, take your function, which is x cubed minus x, and replace the x with c's. Well, okay, I can do that, I suppose. So we really have, not x, but c cubed minus c equals 1. That's really what it's asking. Go ahead and use a calculator to solve this equation. Well, how do we solve an equation like that using your calculator? My calculator doesn't use c's, I'm going to use x's, but it's always very easy you just set one side in y1 and one set in y2, left side in y2, and we're going to see where they intersect. So, you can't see that. Okay, so I've got x cubed minus x and 1. I'm just going to do a zoom standard. This is on the interval from 0 to 2, so technically I'm going to go ahead and just change my window so that I'm only looking between 0 and 2. I also know that I don't need to get very high based on this graph. I'm also going to go ahead and change my y's just so I don't have to look at too much information here. I'll go from -2 to 8 maybe. All right, so now I'm looking at just what I need to look at. And I can see the intersection there, so I'm just going to do a calculate the intersection and move Tinkerbell there and do enter, enter, enter. Definitely the fastest, easiest way. So we get C equals 1.3247. You good? I heard an O.
Yeah, my calculator.
Oh, did it? Okay. All right. Again, on the AP test, you must have 3 decimal places at least. Okay.
So I would have been fine, like, if changing my, because you can change your calculator to 3 decimals always.
I would not do that. Don't do that. So you don't even have to. So for instance, the answer of 1.324 or 1.325, either one of those earns credit. Mine earns credit even if I wrote it wrong and I wrote 1.324983117. The readers actually stop looking. So they are trained to say, oh, stop right there. We don't look at anything past the 3rd decimal place. All right, so they, even though that's totally wrong, nothing close to what it doesn't matter, okay? They stop looking, and so it's called truncating. You can truncate your decimal, so you just chop it off after the 3rd decimal place, or you could round if you want. They're both correct. And so that's a good question. I would say, just in general, mostly because of how a lot of questions work, you don't want to round off early. So when you can, use the store feature and store a big long decimal, like we were sort of doing with solving differential equations. We'll practice more of this too, but store those big long decimals, or at least carry 5 decimal places. Use 5 to get a 5 is sort of what I say. Carry 5 decimal places through your problem, and don't do less than that until the very end. Okay. But we will do more of that as we review. Okay, so we have these accumulation. So integrals, we know, represent areas under a curve. And we like to use that to sort of interpret what everything means. So in lesson 4.1, you interpreted rate function models, and we can now revisit this topic to include the concept of accumulation of area, or whatever we're talking about in this case. The graph at the right models the rate of rainfall. So this is a rate of rainfall. So imagine you're sort of looking at a derivative function, right? It's a rate of change, okay? You can look at the units here, inches per hour. That is like a slope. All right, so when you're interpreting things now, you have to think, what am I looking at? Am I looking at an original function, or am I looking at a derivative? And here we are looking at a rate of change, looking at a derivative. All right, inches per hour from midnight until 6 a.m. So this is time in hours after midnight. When you're given a graph, guys, make sure that you really spend your time figuring everything out, looking carefully, reading those units, and figuring things out. So we want to write a complete sentence to explain what point A on the graph represents. represents. Include numbers and units in your answer. To this and examples 8, 10, and 12. So numbers and units in your answer. Okay. All right. So point A. Here's point A. What is point A? If I were to give it an ordered pair, it would be 3, 1. Okay. Great. Good. Point A is 3, 1. So what does that mean in terms of this graph? Yes. At 3 hours after midnight, yeah? All right. So at 3 hours after midnight, and of course at 3 hours after midnight, that's also known as 3 a.m. So either one of those would be appropriate statements. At 3 hours after midnight, the rain, what did you say, Luke? I remember he's so short, aren't they? I'm going to say the rain is falling at a rate of 1 inch per hour. So again, all we're doing is interpreting what this ordered pair really means based on the actual units, okay? So not too bad. All right, what is the slope? What is the slope of the graph between points B and C? -1, better. All right, so the slope is, we are going down. Now this is where I get screwed up all the time, okay? From B to C, we are going down 1, 2, 3, 4, 5 boxes, okay? But don't put down 5 because it's not down 5. Because we went from 1 to 0. Okay, I do that all the time. I simply count the boxes and like it's down 5 over 1. No, it's not. We started at 1 and we're going down to 0. So it is down 1 over 1. And our units, if we were to include units on that, I might just do this. Down 1 over 1, that's my slope. If I go down 1, those units are inches per hour. Yeah, and then the over 1, those units are in hours. So it is -1 inches per hour per hour. And I just like keeping it in that form, inches per hour, just because it's so easy, it's so straightforward. Yes, of course, it means inches per hour squared. So that also works. All right, write a complete sentence to explain the meaning of your answer to number 7. So what do we think that slope means? It's hard, isn't it? Like, what does it really mean? So at B, we were raining. It was raining at an inch per hour. And at 5 a.m., you're right, it's not raining anymore. Like, it's 0 inches per hour. So what happened to the rainfall in that time period? It decreased? All right, so when we're talking about the slope of a function, you can see our function is going downhill, so it is decreasing. Our function is decreasing, so our rate of rainfall is decreasing. Between points B and C is the time period between 4 and 5 a.m., so we're going to start with that. Between 4 and 5 a.m., the rate of rainfall is decreasing. The rate of rainfall is decreasing at a rate of 1 inch per hour per hour. I hate this stuff. This is the thing I'm the worst at. How many rates do I need to say? Okay. The rate of rainfall is this function that we're looking at, okay? And then when we take a slope, that is another rate. I don't need to say the negative because I used the word decreasing. So I wouldn't want to do decreasing at a rate of negative 1 inch per hour per hour. That would be wrong, all right? That'd be a double negative, so that would reverse itself. So it's decreasing at a rate of 1 inch per hour, which would make sense. We had rainfall, but then it went away, so it had to decrease over time, okay? So that does sort of make sense. Again, let's look at the integral from 3 to 5. So between 3 and 5 of our function here, remember, what is an integral? It's an area, all right? So again, whenever you see a derivative, you're thinking slope. Now, whenever we see an integral, we're thinking area under the curve, okay? Those are the two things you need to think about. Do you have a question, Maggie? Okay. All right. So how do we find the area between 3 and 5 of our function here? What do we do? We don't have like an explicit function, right? But we have shapes, don't we? Okay, so we're doing shapes. So that's what we're doing. We're splitting it up into recognizable pieces. And so that would be equal to, let's see, it looks like I've got a rectangle there. I'm going to split it up. So that would be a base of 1 and a height of, 1. Look at that. And then I have a triangle, which should be 1/2 base times height. So I have a base of 1 and again a height of 1. Well, that's very, so I get 1 plus 1/2 or 3/2. So before I do number 10, I want to think about my units. And I really love this. And the more I teach calculus, the more I think it's just amazing. Again, this is area because R of t gives me my height. It gives me the height, my boundary of how tall my function is, right? And dt, the change in t, the change in time, gives me my width, okay? And that's how we get area, all right? Base times height, that's all it is, okay? The nice thing is we are doing units here. If I'm multiplying height times width, well, my height, the units are inches per hour. And when I look at the width, what are the units? Hours. And so when we think about units there, what happens to inches per hour times hours? The hours cancel out and we're left with inches. And so what we've got here is, wow, so that means this shaded area, when we find that integral, when we find that area, we're looking at how much rainfall, inches of rainfall that we got between 3 and 5 a.m., okay? And when you think about it like that, that is the complete sentence. So, between 3 and 5 a.m., it rained a total of 3/2 inches. So that is the accumulation of the rainfall. All right, does that make sense to you? All right, so soup, I think, this is like the biggest thing for me is what we can learn just by analyzing the units, okay? And I think that that's amazing, okay? So this is the accumulation of rainfall, and that's why we call integrals accumulation functions, okay? So we are accumulating rainfall in our rain gauge, and we can see that it rained between 3 and 5, a total of, 1.5 inches, really. All right, let's approximate the value of the integral from 0 all the way to 6 of our function here. So again, this is area under the curve. Well, how do we approximate the value using geometrical regions? We did a shaded region already. How do you suppose we can approximate this first part where it's all curvy-like? Riemann sums? So we could, if we wanted to, we could absolutely maybe use, I don't know, trapezoidal sums maybe are best. Do you suppose I could, like, what if I just started at the beginning and drew a line to the end? Is that a pretty good approximation? Right? It looks like a pretty good approximation there. I think that kind of works. So, all right. So then it's approximately, because they use the word approximate, I'm also going to use an approximation sign, not an equal sign, though they don't deduct for that. It's just me being picky with words. So here I have a triangle, so I'm going to do 1/2 base times height. My base is 3, and my height is 1. And then plus our shaded region from 3 to 5. Well, we already did that. That was 3/2. And then from 5 to 6, it's nothing. So I maybe just should put a 0 on there. But you don't have to, of course. All right, so we have 3/2 plus 3/2, which is 6/2 or 3. All right. And again, if I'm thinking about my integral, once again, I'm thinking to myself, all right, again, this is area under the curve. And if I'm thinking about units, what are the units of my height function here? Inches per hour. And my width units is time, so hours again. And once again, this would be 3 inches. So what does that mean? Write a complete sentence to explain the meaning. I'm going to start with the word between. Between. What time? Midnight and? Yeah, midnight and 6 a.m. What did we get here? What does that integral represent? It rained a total of 3 inches, or approximately, I guess if it rained a total of 3 inches. Gary wrote it rained approximately 3 inches of rain fell. All right, so any sort of, we could maybe put in the word approximately. That would be best. All right. It rained a total of approximately 3 inches. All right. So anything about that? Any questions about that? All right. Good. Hopefully that's clear. Really, I'm hoping that you understand the units, because that can make a world of difference. If we were to ask the average value of the function, so I want to talk about that really fast. If we were to ask, what's the average value of R of t from, let's say, 0 to 6 a.m.? Let me do that in pink. The average value of R of t would be 1 over b minus a, so 6 minus 0, from 0 to 6, R of t dt. Let's analyze those units just really quick here. We know, because we've already done this, from 0 to 6 of R of t, those units are simply inches. So we did those right here, right? But this 1 over b minus a that we're multiplying by, what are the units here? 1 over, what are these, 6 minus 0? Hours. So 6 minus 0, those are hours numbers. And so when we look at the units again, we're back to inches over hours. And so when we talk about the average value, we're back to the same units that we started with on the function, okay? So again, that's saying that the rate of rainfall, so the average rate of rainfall, in this case would be 3/6, or 1/2 inch per hour. All right, so the average rate of rainfall from midnight to 6 a.m. was 1/2 inch per hour. That's what that means. Does that make sense to you? Okay, I hope it does. Okay, I'm sure you have lots to do. I think Delta Math today.